Hello, in this video I want to look at Chapter 22, Sections 1 through 4, kind of a introduction to magnets and magnetic fields. So kind of starting with some basics here. If we think back to elementary school or whenever we first played with magnets, we learned they had a north pole and a south pole, and it didn't take us very long playing with them to find out that one end of the magnets would stick together and one end of the magnets would push apart. So we have unlike poles, they attract each other, they want to stick together, get closer together. If we've got like poles, they want to repel and push apart. Okay. Kind of another basic thing, if we had kind of cheap magnets in elementary school and we dropped it and broke it in half, we found that we didn't actually have just a north and a south still. We actually ended up with two magnets, one with the north and south and the other one with the north and south. Okay. And if we keep that process going, if we keep snapping the magnet in half, we actually keep ending up with smaller, weaker magnets. Okay. If we kept doing that all the way down as far as we could, we would actually end up with just a charged molecule with a south pole and a north pole. Okay. We can't break it up to where we have a north pole and a south pole separate from each other. If we talk about materials that can be attracted by a magnet, it's called ferromagnetic. So like iron, cobalt, nickel, some of the rare earth magnets like neodymium magnets that you might have heard of. Any of those metals that are magnetic can be turned into a magnet. Okay. One process for doing that is you take two stationary poles here, a north and a south pole, and in between them you suspend your piece of ferromagnetic material. And then you heat it up, and as you heat it in the presence of those north and south poles, the kind of domains inside of the magnet are going to line up. So as it just sits, if it's not a magnet yet, you've got all of these domains that kind of little magnets inside of the big piece of metal. And so they're all different sizes and all different directions, and they kind of cancel each other out, so they don't have a very magnetic effect. But if we heat it up and then let it cool in the presence of those magnets, then we actually end up with a magnet itself. All of those domains kind of align, and next to the north pole of our stationary magnet, we get the south pole of our new magnet, and vice versa. Okay, so that's one way to create new magnets. While I'm here, I was going to talk about electromagnets. And so if you take a piece of ferromagnetic material and you wrap it in a conductor and feed current through it, you end up with a electromagnet, which is typically a lot stronger than what you can get from just a permanent magnet. The more current you feed through it, the stronger the magnet gets. To a limit, of course. Eventually, things start to either melt or the metal itself overheats and it loses its magnetism. Next thing we want to look at is kind of field lines within a magnet. So if I've just got a normal magnet here, if I were to approach it with a compass, whatever direction the arrow on my compass points, that's where the direction of the field line is. And so if I were to map all the way around this, I would find that as I move down the magnet, the needle of that compass turns around and eventually is pointing back that way. So I'd end up with a field line like this. And obviously there's only got two drawn here, but I could go on all sides of the magnet and I would end up with these field lines all the way around. If you look at this one, it really looks a lot like our electric field, and it's very similar. One major difference is that if I were able to probe inside of the magnet, my field lines would actually make a complete loop, whereas our electric field, they started at one end and stopped at the other. Magnetic field lines make a complete loop. Okay, kind of getting into the meat of the section here. We've got what's called a Lorentz force. If I were to have a magnetic field and pass a charged particle through it, that particle is going to experience a force from the magnetic field. So that force is measured in newtons. And the rest of our formula here, we've got our charged particle, so same variable as we used for electric fields. Again, that's measured in coulombs. We've got our velocity in meters per second. We've got the strength of our magnetic field. That's measured in teslas. Now, that's kind of a new unit for us. It's just a way to measure the strength of a magnetic field. If you look in the reading, you can see all the units involved with that. For a little bit of reference, bar magnets, really strong bar magnets can have a strength of 2 teslas. So weaker ones, a half, 1, anywhere in there. The Earth's magnetic field is only 5 times 10 to the negative 5 Teslas, so very weak, the Earth's magnetic field, which is why, pieces of metal don't stick to the ground. And finally, we've got this sine of theta, where theta is the angle between our velocity and those field lines. Okay. So it can be kind of hard to keep track of what direction that force is going to be, but we've got what's called the right-hand rule. So if I've got, say, a magnet here with our north and south and our field lines, we've got these field lines. If I were to move in here with a charged particle, so if my velocity was that way, I can use this right-hand rule to try to figure out what direction the force is in. So I'll come back to this one. This one's a little bit easier to demonstrate. If I've got my field lines going this way and my particle moving to the right-hand rule says that if I put my fingers in the direction of the magnetic field and my thumb in the direction of the velocity, then the force, this Lorentz force, is going to be perpendicular to those, so coming out of my palm. So in this example that we've got drawn out down here, with the velocity going to the right and the field lines going up, the force is going to be coming up out of the page. And since I'm not very artistic, and most people aren't, we can represent this force coming up out of the page as a circle with a dot in it. It'd be like an arrow coming up out of the page. If, for example, the force was going down into the page, it'd be a circle with a cross through it. So if we go back to the little picture I sketched out here, if I've got my field lines going towards me and the velocity going to the left, I can't really bend my hand that way, but again, our Lorentz force is going to be coming up out of the page, because it's essentially this other one just flipped around. So again, the force is going to be coming up out of the page. Okay. So that's kind of how the right-hand rule works. We'll look at a couple examples of that. Okay, so we've got 3 different situations here, and I didn't mention earlier, the right-hand rule applies to positive charges. If we wanted to apply it to a negative charge, it's just the opposite direction, I think is the easiest way to think about it. So here we're going to look at positive charges. Here I've got my magnetic field, again with the x's, that means going into the page, my velocity going to the right. So if I try to orient my hand here, I probably can't show it on camera very well. But the field lines, your fingers are the field lines, there's more of them going into the page, and my velocity going, I can't really show you that, but velocity going to the right. So that means my force coming out of my palm is going up. Okay, up on the page. If we look at this one, notice I've got my field lines going off to the right, velocity to the left. So if I were to try to do that, I'd have to have my fingers going that way and my thumb pointing straight back from my fingers. So not only would that be painful, but if we just think about the formula, it had a sine of theta in it. And if you look at this, the angle between these, you can either say that it's 0 or 180, either way. Sine of that, so sine of 0 is going to be 0, and sine of 180 also 0. There is no force on this one, okay, because the velocity and the magnetic field lines are going opposite directions. If we look over here at this one, we've got our magnetic field going this way, so I've got my fingers going to the left, and velocity is coming up out of the page. So I need to stand my hand up with my thumb pointing straight up, and my palm is pointing back at me. So that means my force is coming down the page. Okay. So not the best medium to try to demonstrate the right-hand rule. But here we've got kind of the different situation where we can still use the right-hand rule to look at it. So again, we've got a positive charge, and we want to know the direction of the velocity this time. We've got the magnetic field, and we've got the force. We want to find the velocity. So just like before, I'm going to use the right-hand rule. Here I've got the magnetic field lines coming up out of the page, and the force is going towards the top, which means my fingers would be pointing up and palm out because the force would be going out. So then my velocity, when my thumb's pointing, is going to be off to the left. So on the next one here, I've got my field lines going to the right, so all my fingers pointing to the right, force going away from me again. So I need my fingers pointing to the right, force away, and my thumb is pointing up. So the force here is going to be coming up out of the page. Or sorry, not force, my velocity is coming up out of the page. I think I probably said force over here too. My velocity is to the left. Okay. One last example here, kind of actually using that formula. So we had my force is the charge times the velocity times the strength of the field times sine of theta. So I need to know the maximum magnitude of the force if I pass a rod through a magnet, between the poles of a magnet. So say that I've got north here and south up here. I would have a set of field lines going like this. Okay. And my rod has a charge of 1 microcoulomb, and the strength of this magnet is 1.5 teslas, and I'm passing it through at a speed of 5 meters per second. So I'm going to think about it as just passing it through this way, straight down through the magnet. So I just start filling into the equation here. I've got my force, 0.1 microcoulombs, so 0.1 times 10 to the negative 6th coulombs, and then my velocity is 5 meters per second, and my strength of the field, 1.5 teslas. Okay, and since I'm going to be coming in perpendicular to the magnetic field lines, theta is 90 degrees, so just 1. So that'd be times 1 if I want to put it in there. If I put all this in and work that out, I would end up with a force of 7.5 times 10 to the negative 7th newtons. Okay. So very small force. Now, if I think about what direction this force is pointing, if I've got it drawn like this and my velocity is coming in to the page like this, I just have to use the right-hand rule and think about what direction it's going. So field lines that way, velocity is going in, my force is going to be pointing out this way. Question's kind of vague, but really we just need to know that the force is always perpendicular to the plane made by the velocity and the magnetic field. Okay, so that's kind of just one application of that formula. One last thing to kind of note about this, since there is that force coming through, if the particle can stay in that field long enough, it's actually going to veer off and start to go in the direction of the force. So in my example here, it would start to veer off and go, I'm coming in like this, it's going to veer off and kind of go to the right, if it can stay in that field long enough, if that field's big enough and it stays there long enough. Now that the stronger the magnet is, the less time it has to be there to feel that effect noticeably. And the faster it goes, the more the effect is, because the force is greater. One other thing to mention here with this formula, if the velocity is 0, there is no force. So if I just have a point charge sitting here in between the two poles, there is no force because the velocity is 0. So just one more thing to think about with this formula. My homework problem, very similar to the examples that I've done here, so hopefully it helps. Thanks.